Alright, so today we're doing the lesson on elastic potential energy. So looking at Hooke's law, let's say we take a spring at its equilibrium position, so that's x equals 0, and we're going to stretch it to some value x. At that point, how much energy is stored in the spring? We know there's stored energy because I could take an elastic band, which is like a spring. It's an elastic material. I can stretch it, and all I have to do is let go, and that energy gets converted into kinetic energy. So we know there's stored energy there. How do we figure out how much? Well, to do that, let's look at the work done, because in order to take this and move it this distance, x, right, we do work on it. Now, here's the tricky part. We know that work is force times displacement times the cos of the angle between them. Well, if our force is in this direction and our displacement in that direction, well, the angle is 0 degrees and cos of 0 is 1. So let's just get rid of that. Then we have force times displacement. Well, force, the force needed that you apply is, well, we learned that in Hooke's law, it's the spring constant times x, and your displacement is x. So if this is all you do, it looks like the work done, and therefore the stored energy, which we call elastic potential energy, is kx squared. However, this is wrong. Can you think of why that might be wrong? Take a second if you need to pause the video. Okay, let's move on. If you need more time, pause the video. But the reason this is wrong is because as you pull it, the force required to pull it a little more changes. It increases, right? It's not a constant force. Okay, we looked at the graph of this. Well, maybe we didn't. But the graph would look something like this for f and x. Right? As you pull it a small distance x, right, it requires this much force, and then this much, and this one. It's a linear relationship. You can see that because the equation is f equals kx. So f as a function of x is a linear relationship. And so what we need to do, right, which we haven't done, but I did mention when we did our lesson on work, is to find the work for a force that isn't constant. We need to find the area under this graph. Now, because that's a nice triangle, well, my triangle isn't a nice triangle, but it is a nice triangle if you draw it properly. Okay. All to find the area on the graph is easy. We just do a half base times height. Now, the height here is your force, right? This is 0, right? And this is, well, if that's x, that's 0. This value is kx. So your height would be kx minus 0. And your base would be x minus 0, so that's x. Therefore, your work done is half, because it's a triangle, base times height, which we get to be 1/2 kx squared. And this we call elastic potential energy. Okay, it's the energy in a spring that is either stretched or compressed. Okay, so now that we talked about that, let's try some problems. Let's try the first one on the back. Now this problem is actually done in your textbook, but I don't like the way how they quickly solve it and make assumptions that they don't actually tell you. I mean, they're perfectly reasonable assumptions, but they don't tell you what they are. So here we have an apple on a spring. There's our apple. And this is our equilibrium position. So let's call this x equals 0. Then the apple is allowed to fall. And at some time later, it falls to a point of 11 centimeters below where it started. So this is our before. This is our after. Sometime t. Okay. Now, the first part says how much elastic potential energy is stored at this point. That's not too bad. Okay, I can just do that quickly for you here. It's plug and play. E equals 1/2 kx squared. They tell you the the spring constants, 9.6 newtons per meter. So we just plug and play 9.6 newtons per meter. And for x, make sure you change it to meters, so 0.11 meters squared. And just plug that in your calculator. 5.8 times 10 to the minus 2 joules. Okay, so part A is not too bad. Part B is the one that can be a little tricky. So let's move over to part B. I need to erase this. So if you need to see it, pause it or go look at the answer sheet. Okay. So what part B is asking for is what's the speed of the apple after it's fallen 11 centimeters? So now you're going to need to do an energy conservation question. We need to figure out what energies are present here and what energies are present there and set them equal to each other. So first, what energies are present here? Well, there's no elastic potential energy, and it's not moving yet. That's like where it's being dropped, so your initial velocity is 0. So what energies are present there? Well, it looks like it's raised in a position in a gravitational field. So it's got gravitational potential energy, right? Since this is the lowest point, it's easiest in this problem to say, okay, let this be a height of 0. Now, if that's a height of 0 and this is 11 centimeters, well, then this is a height of 11 centimeters. Okay, height is always going to be, well, it's a scalar quantity in our equations. X is not, though. But to make things simple, we can just make down to be a positive x direction, which is why I label that to be positive 11 centimeters. This is great because now they're both x and h are 11 centimeters, and this is going to make rearranging our equation a little bit simpler, which is what the textbook does without telling you. All right, so here we're going to do all the energies before equals all the energies after. Now, before we said we had gravitational potential energy, all right, so we have EG. What do we have after? We don't have EG because we decided to set that as a height of 0. So we don't have EG. We don't know if that's the lowest point it reaches, though. It doesn't say that's the lowest point. So the velocity is not 0. If it were, then we'd be finished the question. So it's definitely got kinetic energy. And it's also having its spring stretch, so it's got elastic potential. So we have both kinetic and elastic potential. So gravitational gets converted into kinetic and elastic potential. All right, so now let's write our equations in for each. This is mgh, and we know all those variables. This one's a half mv prime squared, and this is a half kx, we'll call that x prime squared. Now the interesting thing is we do know that h and x prime are the same. So your textbook, I think, just writes it all as x. And so they sort of skip this step and just write mgx equals a half mv prime squared plus, and I'm just going to leave that as x, a half kx squared. Okay, and this is where I usually get a lot of students asking me questions like, why is the gravitational potential energy mgx and not mgh? Well, that's why. It is mgh, but in this case it works out that x equals h. All right, so there's only one thing left to do, and that's to rearrange the equation. So we're going to have v prime. I'm running out of board room, so is the square root. You can't cancel out the masses because there's no mass in that term. But we can write it as 2 mgx minus kx squared, and then divide each term by m, or just the whole thing by m, like that. Now you can make that simpler if you like. Since you can factor out an x, you can cancel an m in this term, but then leave it over here, so we can get the square root of x times 2g minus k over m. That'll work? Yeah. Well, no. Yeah, that works. Okay. And then you just plug in all your variables. Make sure you change your units to SI units, and you'll get 1 meter per second. Okay, so that's that question. If you need to see it, take a look, pause the video. I'm about to erase it all. We're going to go to question number 2. Question number 2 is based on a fun activity we usually do in class where we launch springs at targets. Sorry. But I mean, you can easily do it at home with an elastic band. First, you need to know the spring constant of the elastic. So if you have some known weights that you can attach to it, right, or just take some weights and weigh it on a kitchen scale, attach it to it, right, measure the x that it extends by, that it stretches by, and then knowing the masses of your weights, you can figure out what the force is. Take Hooke's law, since you know force and x, figure out what K is, and then once you know K of your elastic, well, you can do something like this. Don't shoot people, shoot targets. Okay? Alright, so we have a group of students participating in annual Spring Wars contest. Is given a spring in the following challenge. Launch the spring so that it leaves a launching pad at an angle of 32.5 degrees above the horizontal and strikes a target at the same elevation, a horizontal distance of 3.65 meters away. Friction and air resistance are negligible. Calculate the stretch needed for the spring to reach the target if the spring's mass is 15.4 grams and its force constant is 28.5 newtons per meter. Okay. So we got a couple parts in this question. Okay, we're going to have our spring, which is going to be stretched. Okay, and so let's just call that situation 1. We have stretched spring. And situation 2 is when it's going to be launched. So launched spring, which becomes a projectile motion question, which hits a target. Okay, now for projectile motion, when we did projectiles, we did like a golf question, which is on a flat surface, and I derived an equation which you could use as your range equation, which is also derived in your textbook if you wanted to see it. But it's delta dx equals vi squared over g times the sine of 2 theta. You may or may not remember that. But this is the equation that proves that the optimal angle for maximum range is 45 degrees, because the sine of 90 would be 1, and therefore theta needs to be 45 degrees, so that 2 theta is 90. And that will give you your largest delta dx. So that we're going to use for projectiles. Okay? And based on that, calculate the stretch needed. Okay. So we don't know initial velocity, but we know range, we know gravity, and we know the angle. So we don't know initial velocity. You could just calculate initial velocity, but let's go to step 1 first. And we're going to have an energy conservation question. The energy conservation is the 2 points, 1 and 2. 1, when it's stretched, and 2, when you launch it. Okay, so initially when it's stretched, well, what energies do you have present? It's all elastic potential. And then the instant you launch it, that all gets converted to kinetic. And this is before it actually goes along this parabola. Okay, it's all kinetic right at the beginning. So all the elastic energy gets converted to kinetic energy. So that's 1/2 kx squared equals 1/2 mv prime squared. Now the important thing to realize is that this final velocity in this equation is the same as this initial velocity in this equation. This is where a lot of students get confused. Like, how can vi be equal to v prime? Well, they're different situations. For example, this v prime is between 1 and 2. So this v prime is the velocity at 2. and 2 is the instant the spring is launched. So in our projectile question, the instant the spring is launched, we call VI. So they're the same. So we can actually simply, instead of solving numbers for this one, we can just rearrange for VI squared, which equals delta dx times g over the sine of 2 theta. We can take that and substitute it into here. The halves are going to cancel. We get kx squared equals m times delta dx times g over the sine of 2 theta. Right? And then the question is just asking you to solve for x. Okay. So divide both sides by k. Take the square root. And plug in everything you know right there. And you should get 0.146 meters, or if you prefer 14.6 centimeters. All right, so we'll see you for the next lesson.